Okay, chapter 16 focuses on climate change, what we know and how it impacts our oceans. So first, what we know, climate has changed over Earth's history. So this is the past 800,000 years, and you can see that climate fluctuates. During the periods shown at the top with the red bar, those are interglacial periods. All the rest of the time are glacial periods, the ice ages. So only recently have we come out of an ice age, and you can see most of the relatively recent past, the Earth has been in an ice age. Now, how do we know this, and how do we measure the temperature change 800,000 years back? That would be the question. The way that we do this is by looking at bits of the atmosphere that are then trapped in ice. Okay, so if you look at all forms of ice, snowflakes are 90% air. So as it snows in an area, it also traps some of the air and then gets compressed over time into ice granules, firn, and then ice. Even ice has 20% of its volume as air bubbles when you melt it. So this then allows us to basically go through ice cores and look into the past and see what the air that was trapped in there looked like. So the way that we do this is by finding areas that have deep ice cores. So Greenland is a good example, Antarctica. Some of these cores are 3,500 meters deep, 11,000 feet. So you can drill, and as you go, each of the layers basically gets deposited in a given year, and you can work your way back into the past by taking little sections of the ice core, placing it in a container, and then melting it and trapping the gas bubbles that are released from that. Then from there, you can measure their oxygen isotopes. Because the ratio of oxygen 18 to oxygen 16 tells us something about the temperature. So oxygen 18 is a stable isotope of oxygen. It has 2 extra neutrons than regular oxygen, which has a total of 16 protons and neutrons in the nucleus. So add 2 extra neutrons, it's still stable, it's not radioactive, but it's heavy oxygen. When the atmosphere is colder, there's the sites that are colder tend to have less oxygen 18 and more oxygen 16. When it's a warmer temperature, there's a higher ratio or a higher amount of oxygen 18. So this can be used as a thermometer looking back in the past, and it can kind of be ground truthed with recent years of deposition. Okay, what else do we know? Several natural processes affect climate. There's human effects, but that's not what we're talking about here. We're talking about just natural variations in the earth that can ultimately impact the climate. And so every 100,000 years, the earth is going, as it orbits around the sun, is going to vary in the shape of its orbit to be more elliptical or more circular. So the blue orbit, as you can see on the left-hand side, is more of an ellipse compared to the red orbit. And over 100,000 years, it's going to go from that elliptical orbit to the round orbit and then backwards. Every 41,000 years, the angle of tilt of the Earth's axis varies between 22 degrees and 24.5 degrees. And every 200,000 years, the Earth's rotational axis shifts. This can affect climate. It changes the solar input that's coming through solar radiation. If you follow the more elliptical orbit, there's going to be times of the year that it's further away from Earth, for example. If it shifts in its angle, that can potentially impact the amount of solar radiation that the Earth gets. Some other natural processes that affect climate are changes in albedo. If you have parts of the earth that are covered with ice, that reflects 70 to 90% of the sunlight, whereas oceans by themselves only reflect 10% of sunlight. And remember back when we looked at the atmospheric processes, we did that because of the linkage between the ocean and the atmosphere. Same sort of thing with climate. Climate affects the atmosphere, but climate also affects the oceans, and vice versa. Oceans are going to absorb more sunlight, glaciers and sea ice are going to reflect more backwards. So this ice cover affects the reflectivity, and that affects the amount of solar radiation. If it reflects it back, it just goes back into space. Versus if it's absorbed by the ocean, only 10% is reflected back, then that has greater potential to heat the Earth's surface. Same sort of thing, land versus land covered by a glacier. The glacier is going to help reflect more of the ice. So the ice also insulates the ocean from heat exchange with the atmosphere. And the seasonal freezing and thawing helps to moderate the temperature through the latent heat of freezing and the latent heat of fusion. So in all of these ways, having ice covering a portion of the ocean contributes to this differential heating of the Earth's surface and helps to keep it in a cooler temperature. As climate warms, then we lose that potential to reflect some of the sunlight back. Some other natural processes that affect climate include changes in the composition of the atmosphere due to volcanic eruption. So a volcano erupts, it emits sulfur dioxide, HCl, ash into the atmosphere. These basically block some of the sunlight and can cause short-term cooling. We're looking at this on the effects of about a year. Before these ash particles all settle out, the aerosols settle out, and then no longer have an effect on it. So they do have an effect, but it's relatively short-lived compared to other factors. We also know that the composition of the atmosphere can affect the climate. If you take a look at this time series, looking at the current temperature, then the cooling period of the Ice Age, the warming period during the interglacials, you can see that the fluctuations there, when it's warm, it tends to have higher amounts of methane, higher amounts of carbon dioxide. When the Earth's temperature is cooler, it tends to have lower amounts of carbon dioxide, lower amounts of methane. Methane is a greenhouse gas that is much more potent than carbon dioxide. So even tiny changes in methane can have big effects on temperature. You'll also notice that the current values for both carbon dioxide and methane are beyond the scope of what we measure in the past, even during the spikes during the interglacial period. During the last interglacial period, the CO2 concentration was 280. It's currently over 400. Same sort of thing with methane. Methane was at about 700 parts, 6 to 700 parts per billion, and currently we're at about 1700 parts per billion. So this is affecting climate. These things are affected by other processes like plant growth can take up carbon dioxide and things like that. Thawing of the permafrost can release methane, things like that. So any changes in the composition of the atmosphere can potentially affect temperature. All right, so what are these greenhouses? Carbon dioxide, and what are their sources? Carbon dioxide is released into the atmosphere by fossil fuel combustion. Basically, this carbon dioxide was taken out of the atmosphere when the coal was formed, when the precursors to petroleum were formed, and that then locked it away from the atmosphere. Now we are removing these fossil fuel sources, combusting this fuel and putting that back into the atmosphere. Forest fires also release large amounts of carbon dioxide. Methane is released from rice farms. If you've ever been out to a lake and you've seen little bubbles come up, and the bubbles kind of smell like rotten eggs. The rotten eggs are sulfur dioxide gas. It's released by the sediments because there are certain bacteria in the sediments that will convert organic material into different forms, and then they'll convert sulfur from one form to another. So the resulting gas that bubbles up from the sediments, especially if you've walked out in muddy sediments and you felt kind of bubbles coming up your legs, that included methane in there, and it's a partial decomposition of the organic material. And this can occur pretty substantially in rice farms. It also occurs in the guts of cows, releasing methane into the atmosphere. It can occur from landfills and from fossil fuel production. All of these can release methane. So some landfills will actually capture this gas, kind of cap the top of the landfill, capture this gas, and then they can burn it as a supplementary source of fuel. This is basically natural gas. Methane is natural gas. And then this can help to supplement. It can be a supplementary source of fuel. When the methane is burned, it converts to carbon dioxide, which has much less of an impact. It has an impact as a greenhouse gas, but less than an equivalent amount of methane would. Nitrous oxides also released through fossil fuel combustions from fertilizers and from livestock waste. And then chlorofluorocarbons primarily impact the ozone layer. That's the primary impact that they have on the environment. As they're released, the chlorine is released from them in the upper atmosphere, and that can degrade ozone and lead to ozone depletion and increased ultraviolet radiation. They also do work as a greenhouse gas. They functionally are trapping extra heat as a part of that. But understand that the two effects are separate. The effect on the ozone layer, and then also they are functioning as a greenhouse gas. And primarily this is from air conditioners, refrigerators, and things like that. It used to be spray cans. If you've seen pictures of people back in the 80s that had really big hair, that people would spray stuff, and at the time it had chlorofluorocarbons in the spray cans. And when they realized that this was contributing to ozone depletion, they very rapidly changed that for other propellants. Okay, well, another thing we know is that the greenhouse gases do warm the atmosphere. Rays of sunlight penetrate the lower Earth's atmosphere. They warm the Earth's surface, and then this heat is reflected back into space. Some of it then is reflected back by the atmosphere, and so some of it's trapped. And this is like a blanket keeping the Earth warm. Without that natural greenhouse effect, Earth would be 91 degrees Fahrenheit cooler. Much of Earth would not be inhabitable, at least not by us. And so it's good that we have the greenhouse gases to keep the atmosphere warm. What's bad is if we over accelerate that, then it traps more and more heat, and then it leads to more and more melting of the ice caps, more and more warming of the Earth's surface, melting of the permafrost, etc. All right, these are the patterns of recent history. So if we go back and we look at the average during, let's make the 1940s as our zero here. You go back to 1860s, the temperature was half a degree Celsius cooler. And since 1940, the temperature is already 4/10 of a degree hotter. So during this period of recorded history, and the temperature has continued to increase since then, during this time frame, we've basically increased the Earth's temperature by almost 1 degree Celsius. So that's about 2 degrees Fahrenheit. Okay. And these are measured by thermometers. This is not, oh, we took a look at the oxygen 18 to oxygen 16 isotope ratio in gas bubbles that are trapped. This is actual people measuring with thermometers, looking at the global temperature increase during that time period. So we know that our climate is changing 1 degree Celsius during that time frame. The 20th and 21st century temperatures are at their highest level in 400 years. And the warming in the Arctic areas is double that for of the globe as an average. We know that sea surface temperature is increasing. Some areas of Florida Bay have been over 100 degrees Fahrenheit recently, and this is ocean temperatures over 100 degrees during the heat of summer. And this is affecting sea ice cover. It's affecting a bunch of things. So it's shrinking the glaciers. It's melting sea ice. The extent of sea ice sheets are at record lows. During my lifetime, they thought that we would never have an Arctic passageway from the Atlantic to the Pacific. And now, on an annual basis, the ice is melted enough that ships can get through from the Atlantic Ocean to the Pacific Ocean through the Arctic Ocean. Okay, sailing north from the Atlantic Ocean, they're able to make it through there now, when 50 years ago that was not the case. All right, now what I'm going to show you in the next few slides is some direct observations of recent climate change, okay? So the average surface temperature increased 0.8 degrees Celsius between 1880 and 2012. So note that this is a little bit smaller than I just said 1 degree Celsius, but I was talking about 1860 to 2020, so a slightly longer time frame. But this comes from a study that basically investigated climate change in detail for several different metrics. Okay, so what we're going to do is kind of walk through this. It's going to look really, really complicated on the slides, but this is going to show you 1900 through the extent of their data, 2012, 2015, something like that. So the spring snow cover in North America, in the northern hemisphere, fluctuates a lot. But you can see there's a slight downward trend over time. Probably initially it was from 38 million square kilometers covered by snow versus 35. Okay, Arctic summer sea ice extent went from, in the early 1900s, about 11 million square kilometers of ice. Now we're down to almost half of that, about 6 million square kilometers worth of ice extent. Okay, so this is the article. This is the study. It's from the journal Climate Change. And these are multiple complementary indicators looking at climate change. And so on the left-hand side, this varies from 1850 through about 2012. And then on the right-hand side, it's more recent, 1940 to about 2012. So it's a shorter time set. For each of these, they're showing several different data sets, okay? So land surface air temperature, sea surface temperature, marine air temperature, and for each of these, they have multiple data sets. So 4 for the first one, 5 for the second one, 2 for marine air temperature, 6 data sets for sea level rise, 6 different data sets for summer Arctic sea ice, tropospheric temperature, so the average temperature of the troposphere, ocean heat content, specific humidity, northern hemisphere snow cover, glacial mass behavior, et cetera, et cetera, et cetera. So we're going to go through each of these. They basically have the same x-axis, or it's slightly different if it's the set on the right. And I'm going to kind of highlight some of these. One of the things to point to is that in all of these cases, by looking at independent data sets, all the data sets are showing the same basic trends. Okay, and by looking at different aspects, air temperature, water temperature, sea level, all of that's going to have, the data complement each other, and they're basically showing the same basic trends. Like, you warm the air, then there's less ice. Okay, that's the sort of thing we're talking about. Okay, so these are the 3 from the top. As you can see, the land surface air temperature goes from, and again, we're going to kind of normalize this between like 1940 and 1960. Late 1800s, it was about a half a degree Celsius cooler than that. And each of these data sets is shown in different color. Now we're looking at 3/4 of a degree warmer than that average between 1940 and 1960. So over 1 degree Celsius warmer during the time, 150 year, 160 year time frame. Sea surface temperature also goes from cooler than that average to substantially warmer than that average. It was about, let's say, 3/10 of a degree Celsius cooler than the average from around the 1950s. Now we're about between 0.2 and 0.3 degrees Celsius warmer than that. So all in all, the air has increased by a degree to a degree and a half, and the water has increased by half a degree Celsius. The temperature anomaly also showing an increase over time. Troposphere, the temperature of the lower part of the atmosphere, showing an increase. The ocean heat content increasing. And that's 5 data sets that are showing that. Specific humidity, as the air gets warmer, as the atmosphere is trapping more heat, more humid on average. All right, the marine air temperature we showed on the last slide, and specific humidity. The bottom 2 sets are new. Sea level has gone up during measurable time. So again, let me emphasize, this is not, oh, we predict that the sea level is going to rise. This is, we have measurable increases in sea level since 1875. Okay? At that time, between 1875 and say 1960, the sea level went up about 150 millimeters, so 15 centimeters. Since then, it's gone up another 70 centimeters. So over a meter of sea level rise during this part of recorded history. And likewise, through the 1950s, a vast extent of Arctic summer ice. Now we're at a point where it is about half of that, just a little over half of that. Glacial mass balance is down, and then the average snow cover over the northern hemisphere from these 2 data sets, a slight reduction in that. It's variable, but a slight reduction. Here's some pictures though. If the graphs don't tell you the picture, this is Glacier National Park in Montana. Same view, same vista. Take a look at the glaciers in 1911 versus the glaciers in 1998. Okay, vastly shrunk, lots of ice melted in those areas. All right, so how have CO2 and other greenhouse gas concentrations changed? This is from the International Panel on Climate Change. We're especially and this shows long-term data sets again from some of those prior measurements. And then we're going to look at recent history, the little parts in the boxes that have been kind of pulled out. These are from direct measurements. And all of this relates to what we call the Keeling curve. We've talked about this before. Climate CO2 levels have shown a steady increase over time. This is from the Mauna Loa volcano, or the Mauna Loa Observatory. Atmospheric concentrations of CO2 have gone from 315 parts per million to now over 400 parts per million. There's also an annual fluctuation where January, April to July, there's an increase in CO2. Then there's a decline that corresponds with the summer months in the northern hemisphere. So June, July, August, September. There's a reduction in CO2 as the plant growth in the northern hemisphere takes up CO2. And then you have low levels, and then the rest of the year there's an increase in CO2 in the northern. So it's a more respiration in the northern hemisphere than releases that because more of the land mass is in the northern hemisphere. And then in the winter months or in the summer months, then there's plant uptake of CO2. That occurs in every year, but the long-term trend is for there to be an increase in CO2. Okay, if you want to see this animation of atmospheric CO2, click on the YouTube link shown here, or I would encourage you to go to the PowerPoint that's on Blackboard and you can copy this link and check it out. It shows that a lot of the CO2 that's emitted is in the northern hemisphere, and it shows fluctuation over time on an annual basis, and it shows some specific sources that release high amounts of CO2. Developed countries in the northern hemisphere primarily. All right, now looking at CO2, we were consistently around 260 parts per million, and then pre-industrial revolution, maybe 275, 280. Since then, there's been a dramatic increase, especially since the 1950s. Dramatic increase in CO2 concentrations. Now we're over 400 parts per million CO2 in the atmosphere. And this has a big impact on the atmosphere's ability to trap heat. Same sort of thing with methane. It tended to be between 550 and 750 parts per billion. Post-industrial revolution, dramatic increase in methane concentrations. And nitrous oxides, again, stayed consistent and low. Post-industrial revolution, an increase in these concentrations. Okay, so these are these graphs are the ones that I showed before from the International Panel on Climate Change. So CO2, methane, and nitrous oxides have far exceeded the pre-industrial values, and they increased markedly since 1750 due to human activities. Okay, now what do we know? We know that it's very likely that humans have already altered climate. So it's not climate change is going to occur, it's climate change has occurred and is expected to continue to occur. Okay, now they've gone and from this same report, they have basically broken out what portion of this is due to natural effects like volcanoes and things like that, and which of this is due to the amount of CO2 that humans have released into the atmosphere. And without the human impact, just solar and volcanic fluctuations, pretty much a flat line. Add in humans to that, and you get an increase of 1 degree Celsius. Now, this graph then breaks it out. So on the left hand, the far left hand, the gray bar, this is the observed warming trend, about 1 degree Celsius so far. Again, climate change is something that we have observed over the last 150 years, okay? And now then the other graphs then break this out into human influence, other influences, and things like that. And we're going to kind of zoom in on each of these parts and emphasize the different parts. Okay, so on the left-hand side, the kind of summary graph, the first bar shows the total human influence, both from well-mixed greenhouse gases and then other human factors, just solar, volcanic, and increased internal variation, basically no effect. Now, if you look on the right hand that breaks this out, everything that's red increases the atmosphere, and all of these are due to human causes. But anything that is shown in blue actually decreases that. So if you just, that's why on the graph that's smaller here, the total human influence is about 1 degree Celsius. But if you add in just the greenhouse gas effect, that would be 1.5 degrees. But there's other things that we've done, aerosols like sulfur dioxide, that actually decrease the climate impact. Okay? They also acidify the rainwater. So it's not something that, oh, well, let's add more aerosols. Okay, so climate change effects, CO2 has that broken out about 3/4 of a degree. The methane effect is about 1/2 degree increase. Nitrous oxides, halogenated gases like CFCs, which are from refrigerants, small impact, but an impact that's measurable. Volcanic or organic, volatile organic compounds and carbon monoxide, an increase. Nitrogen oxides will decrease the temperature. And then, so if you add these up, this is like 2 degrees Celsius, 1.5 to 2 degrees Celsius, but it's balanced off by things like sulfur dioxide, which are aerosols that block sunlight that actually will decrease the climate impact. So you add all of these together, and you end up with a total human influence of 1 degree Celsius, which matches the observed warming. All right, another threat of increased CO2 in the atmosphere is ocean acidification. So again, pre-1750, we had a stable pH in the ocean. Since then, we've had more carbon dioxide in the atmosphere, which leads to more acidification in the ocean. So CO2 from the atmosphere is taken up by the ocean by physical processes. When it combines with the water, it forms carbonic acid, and then it breaks down to the bicarbonate ions and hydrogen ions. And the hydrogen ions basically affect the pH, the acidity, and by adding more industrial activity, putting more CO2 in the atmosphere, this then means more carbonic acid and more hydrogen ions in the oceans, which then can have an effect on marine life. Okay, so here's an example in a laboratory experiment, a sea butterfly shell. So this is a type of mollusk that has a shell. They place this in seawater with increased acidity, and it basically slowly dissolved over a 45-day period because it goes into solution. It becomes more acidic, and that carbonic acid then dissolves this calcium carbonate shell. Okay, so predictions now for the future. Okay, so these are time series predictions of ocean surface pH. We were in the range of 8.1 to 8.2. It's projected that at best, if we stabilize climate, we could level off at a pH of about 8. If we don't do anything and we increase the amount of atmospheric carbon dioxide, this could go down to a pH of 7.8 or so by 2100. Now, that doesn't sound like a lot, but this is enough to have that effect on marine life. Anything with a shell that is a calcium-based shell can be dissolved by that. Plus, things like coral have a hard time building a coral reef when the ocean gets more acidic. So even a fraction of a pH unit makes it substantially more acidic. And a full pH unit means it's 10 times more acidic. So a fraction of that, it's still greatly increasing the acidity. Potential effects on coral reefs. Can lead to more bleaching because of the warmer temperatures. Warm water temperatures have that effect. Coral will spit out their zooxanthellae, which are these symbiotic dinoflagellates that live inside them, photosynthesize, and help to produce some of the food for the coral. Then that's shared, and the nutrients that the coral polyp traps are then shared with the algae. If it's warmer temperature, they expel them. The coral looks white. It doesn't get enough nutrition because it's not photosynthesizing. The weakened skeletons from increased CO2, which acidifies the water, and it makes it harder for the coral polyps to build their skeletons. Increased damage if the frequency and intensity of hurricanes increases. One of the predictions of climate change science is that if you have warmer temperatures in the atmosphere, it will increase the intensity of hurricanes and potentially their frequency. So that could then, if there's more storms, that could wreck the reefs. Potentially increase rates of coral disease. And we've noticed over the last 30 years, the rates of bleaching and coral disease have increased during that time period. So this kind of goes along with the predictions there. All right, so how much is the ocean surface temperature um, predicted to change? It depends on how much the change is. So these are different scenarios. Do we level this off at 1.5 degrees Celsius change, 2.6 degrees, 4.5 degrees, etc.? At best case scenario, the ocean surface will warm by about 2 degrees Celsius. Okay. And that's since the 1950s. And it's already gone a degree. So this would just be one more degree, which is still a lot. At worst case scenario, if we don't intervene, it could increase by 4 degrees Celsius or more over the next 50, 75 years. And then the sea level increase. We've already seen a measurable increase in sea level rise. This could increase another half meter at best to 1 meter at worst. And then the low likelihood, high impact storyline would include the ice sheet all melting. And then that raises the sea level as well. Some of the other effects on sea level are that the water warms, and as it warms, it becomes less dense, and it therefore takes up the same amount of water, takes up same mass of water, takes up a bigger volume, and that increased volume of the ocean then floods coastal low-lying areas. So where is this going to affect? Uh, Coastal areas and islands are the areas that are most likely to be impacted by this. And many islands are low-lying, some of the ones in Micronesia especially. Plus, we like to build along the coast. We like these beautiful habitats along the coast. We like to have shipping by boat, and this is easily done from port cities. So all of these coastal areas are potentially major urban areas at risk. A local example is Tangier Island. Now, again, in terms of U.S. risk to sea level rise, the city at greatest risk is New Orleans because it's warming and the marsh is sinking at the same time. New Orleans was basically built on marshland, and now many of the areas in New Orleans are below sea level. They have dikes and levees to help to protect these areas. Norfolk, Virginia Beach area is number 2, again, due to land subsidence combined with sea level rise. So it's a double whammy. But let's take a look at Tangier Island. This is a small island community located out in the Chesapeake Bay. They have a different dialect of English because some of the early English settlers set up there and remained kind of in isolation. So linguistically, they resemble their language speech patterns resemble more of colonial England. And this area that is at risk because it's a very, very low-lying island, and as sea level rises, it's potentially threatening. So the island has already lost land due to erosion over the last several decades, and rising sea level and the potential for stronger hurricanes can increase that threat. And it has that historical significance that I mentioned. So this is a link to a movie called We Will Stay on Vimeo, and this features former VW student Cameron Evans. Cam was an EES major and was a kind of like a wildlife guide out there, learned a lot about that, and has done also a photographer, and so does incredible wildlife photography, and has been kind of a spokesperson, local spokesperson for the community on Tangier Island because that's where he grew up. All right, precipitation, how's that going to change? Increased temperatures should increase evaporation from the ocean, leading to more humidity, which we saw in some of the prior graphs, and potentially increasing humidity and precipitation. Satellite data since 1988 shows an increase in water vapor over the ocean of 1% per decade. So by 98, it would be 1% higher. 2008, 2% higher. By 1918 or 2018, it would be 3% higher. And so this is measurable amounts measured by satellite data. The evaporation rates are equal to the precipitation rates. So what evaporates from the oceans ends up in the atmosphere, and then that can lead to more precipitation. So potentially the global precipitation increases, especially in the high latitudes. And then there can be local decreases in subtropical areas and some tropical locations. So there could be shifts. Parts of the globe should get more precipitation because of climate change. Some parts of the globe should get less precipitation because of climate change. It's likely that the storm intensity is going to increase, more likely to see heavy downpours, things like that, increased rates of erosion, risk of flooding and landslide, and predicted increase in time between rain events, potentially. Warmer temperatures could lead to more evaporation. We could also, in certain areas, have an increase in drought. And the annual emissions of this are highest in industrialized nations. So the US and Canada, Australia, New Zealand, some of the countries in the Persian Gulf, around the Persian Gulf, Russia, the developed countries of Europe have a slightly lower emissions of CO2. Places where there is greater reliance on mass transit, like Japan, have lower per capita. They still have a lot of greenhouse gas emissions because they have a lot of people and a relatively high use, but it's not over 20 tons of CO2 equivalents per capita per year like it is in the US and Canada. It's half of that, or a little bit about half of that, between 10 and 15 tons of CO2 equivalents. And then less developed nations are releasing much less CO2 per year in the areas that are in the green. Now, one of the concerns then is that population is increasing in the areas that are green, and these are nations that want to industrialize, which then increases their per capita emission of greenhouse gases. So where does this come from? The total line is shown here at the top. Primarily burning petroleum and coal. Some from natural gas emissions, but primarily it's burning coal for electric production, and then a variety of petroleum uses. There is some due to cement production. There's an overall net impact that releases CO2. The actual curing of cement sequesters CO2, but overall, there's the cement production does have a substantial and measurable impact on CO2 release into the atmosphere, net release into the atmosphere, and that's continuing to increase. So what can we do? How can we reduce greenhouse gases? The big one is reduce our CO2 emissions. Setting international, national, and state policy that promotes fuel efficiency, energy efficiency, switching to alternative fuels. In many places, power companies are doing that because a diversified energy portfolio is good for the financial bottom line. Dominion Energy is investing in solar farms in North Carolina and offshore wind because those alternative fuels are cheaper than some of the fossil fuel sources. There is a lot of CO2 emissions in agriculture and food. If you're eating things out of season, it's probably been shipped in from California or Florida, and or from South America. And think of all the carbon that went to transporting that, so that we could have a banana any time of the year, or so that we could have lettuce or whatever, or asparagus at any point in time of the year, not just when it's fresh locally. And then there are some other proposals to remove CO2 from the atmosphere. Reforestation efforts, add more trees, add more carbon that's in trees. That's a good way to remove CO2 from the atmosphere. And this can be tropical reforestation, mangrove reforestation, urban reforestation. All of the additional growing of trees and plants is taking CO2 out of the atmosphere. Grassland soils are thick and rich and full of organic material, and we've replaced them with agricultural soils, much thinner, and less capacity to hold on to carbon long term. So converting some areas back to native grasslands could potentially sequester and store carbon in grassland soils. And then there's been some calls for what we call blue carbon sequestration in the ocean, such as in kelp beds. Growing additional kelp would take carbon dioxide out of the atmosphere. And then we talked before about the proposal to fertilize the surfaces with iron. This did not have a great net effect on CO2. It increased photosynthesis, but it also increased respiration. And then finally, pumping liquefied CO2 into the deep ocean. Um, by capturing it in some way and releasing it there, it's out of the atmosphere for a while, but what are the effects on the deep ocean? And then what about when these deep sea currents then come to the surface, and now you have all of that CO2 that becomes part of the shallow waters? So these are some major challenges that we face in the next 100 years.